This was a question from the final of December 2017. Question 6c asked us to show that the integral from 0 to a of f of x dx is equal to the integral also from 0 to a of f of a minus x dx. That's for any function f of x continuous on the interval from 0 to a. You might be asking yourself if this has something to do with the fundamental theorem of calculus. And you would be correct, but let's make sure that we're thinking clearly on that. Conventionally, we might say that the integral, the indefinite integral of f of x dx is equal to big F of x. So we have a small f over here. We could say that this is our big F of x, or our parent function that this is derived from. And then there would be some arbitrary constant that we would add as a plus c. Now when we have a definite integral, for in this case from 0 to a, the arbitrary constants would cancel out, so we wouldn't need that. And then by definition of a definite integral, if we have the integral from 0 to a of f of x dx, that's just going to equal big F of our upper bound, which is a, minus big F of our lower bound, which is 0. So that's big F of a minus big F of 0. But you have to be careful. Notice that for the other expression here, I just want to get that in the frame. For the other expression here, you can't just plug a and 0 into your a minus x here. There's a little bit more going on. Watch what happens if you try that. If you try just plugging your a and your 0 into your a minus x function here, what you get is big F of a minus a. If x were a, that would be a minus a, which gives us big F of 0. And that would be minus big F of a minus 0, which would just give us big F of a. But notice that what we got up here with the integral of f of x is not the same as what we got down here when we tried just plugging in to our integral of f of a minus x. Because clearly big F of a minus big F of 0 is not equal to big F of 0 minus big F of a. And it turns out there's not a typo. There is a very simple explanation for this. If you just remember your chain rule, just recall the chain rule from Calculus 1. This says that if we take the derivative of our function big F of g of x, and we can say that our g of x function is the a minus x that was inside of the f of x here. If we take the derivative of big F of g of x, this is going to equal the derivative of f of g of x times the derivative of g of x, or f of g of x times g prime of x. So like we mentioned, we'll say that g of x is our a minus x function, and that means if we take g prime up here that we're multiplying all of this by, well, g prime is just going to be the derivative of a minus x. A is just a constant, so the derivative of that is 0, and then the derivative of minus x gives us negative 1. So in other words, the output of the function that we saw before, it was already multiplied by some negative 1. So when we're taking the integral, we have to keep that in mind when we're going backwards. So we could say that our integral from 0 to a of f of a minus x, we could divide the whole thing by negative 1, or we could just multiply it by negative 1. It's kind of the same thing. If we multiply, in fact it's exactly the same thing. If we multiply negative 1 by big F of 0 minus big F of a, well then these just swap around and we have big F of a minus big F of 0, which is what we saw before in the other integral. So hopefully that wasn't too confusing. I want to offer you a little bit better geometric interpretation of this. So let's just go back and just clarify here what it is that we're trying to prove before we go any further. We're showing that the integral from 0 to a of f of x dx is equal to the integral of 0 to a f of a minus x. Alright, the first case of this is when a is positive. If you just imagine here we have a number line, it goes all the way from 0 to a. X is going to fall along this interval just by definition. So x is going to be anywhere in here between 0 and a. We're moving in the positive direction. So x is always going to be smaller than a. So anytime you subtract x from a, it's still going to be positive because there's never going to be an x that's large enough to overtake a and make a minus x negative. Case number 2 is when a is negative. So notice our number line is going in the negative direction here, and we're looking at from 0 to negative a. X is going to fall anywhere along here. Then we could say that for every x in our interval from 0 to a is going to be smaller than x and x is going to be smaller than 0. Or another way of thinking about it, a is going to be more negative than x and x is going to be more negative than 0. So when we have an expression like this, a minus x, keep in mind that your x here is a negative, so this would be minus a negative, and minus a negative gives us a positive. So we're adding some positive term here to our a value, which is going to make it slightly less negative. So in other words, if we took the absolute value of a minus x, or minus some negative value that's less negative than the a, the absolute value of this business here would be smaller than just the absolute value of a. So the argument works out the same for both cases, but let's just keep it simple here and just assume that a is only positive. Again, we have two number lines. Here we have from 0 to a, and this number line represents all of our x values, our x inputs. And here we have another number line juxtaposed from 0 to a, and this represents all of our a minus x inputs. And I want you to notice that for every a minus x value here, you're going to see that there's a corresponding x value moving in the opposite direction. For example, here we have a minus 1, and that is going to, if you just do the algebra here, that's going to equal 1. Well, you go over here and we have a 1 here when x is equal to just 1. So in other words, the input of this function here is the same as the input of this function over here. Similarly, if a were equal to x, well then a minus x would just be 0, and that would take us all the way over here. So we have the same inputs as we do up here. They're just going in reverse order of one another. And obviously the function f, it is going to produce the same output for both. We're just going in opposite order. So in other words, and this is really the meat and potatoes here of what I'm getting at. The graphs produced by f of x and the graph produced by f of a minus x along our interval that we care about, these are going to be perfect mirror images of one another. They're just going to be overlapping. And as an example here, you just imagine that we have, I'm going to zoom in a little bit, Imagine that we have a parabola defined by x squared along the interval of 0 to 2. Well, then our mirror function is just going to be 2 minus x squared. So squared is the function, and then we're just plugging 2 minus x instead of x, in place of x. And if you think about it, you'll realize that the area under each curve is going to be the same, even though they are mirror images of one another. And this kind of makes intuitive sense. If we have a geometric shape like a triangle, well, obviously the surface area is going to be the same when we flip it over. It's just going to be a mirror image, but it's going to have the same surface area. So what we've shown geometrically here is the premise that we started off with, that the integral of 0 to a of f of x dx is equal to the integral of 0 to a of f a minus x dx. We could take a look at another example. Obviously, parabolas are kind of simple. Even if the integrals are, even if part of the integrals go below the x-axis, so part of the integral is negative, the areas are still going to be the same. Notice you have a negative area here that's equal to a negative area here. You have a positive area here that's equal to some positive area here. And obviously the negative areas get subtracted from the positive areas, and equals minus equals are going to equal the same. This was just a natural log function of 1/2 plus x. That's our function there. And then if we just plug, instead of x, if we just plug 2 minus x, then we get our mirror image here in red. So even though it might seem a little bit counterintuitive, and hopefully you appreciate the sort of broader geometric implications of this, we have just proven, both notationally and geometrically, that the integral of 0 to a f of x dx is equal to the integral from 0 to a of f of a minus x. And that holds true when f is continuous on the interval from 0 to a.